Thank you for inviting me. As said, will talk about an analysis that I performed on using OSG, and I'll start off talking about some background of the science, and then towards the end dive into details of the actual analysis that I performed, and maybe some lessons learned and reasons why I wanted to use OSG. And I should just say right off the bat, I'm a bit of an outlier if everyone in this session is representing a collaboration. I am a member of the LIGO collaboration, have been since 2014, and I received this invite through basically channels of trying to find someone in the LIGO collaboration that has run analyses on OSG. And there's been a lot of work by folks both on the LIGO side and on the OSG side to integrate LIGO resources into the OSG. But those are not the resources I use. So I am here to talk about analysis I performed with some other external collaborators. But I think a lot of the lessons learned and a lot of the details are more or less identical to what you'll see from collaboration-based searches. So with that out of the way, let's start off. So I analyzed 6 months of public LIGO data using the Open Science Pool. LIGO data, so specifically I analyzed it for gravitational waves. And my background is going to begin with talking a bit about those. So before we can talk about gravitational waves, we have to understand gravity a little better. And to understand gravity, we have to talk about general relativity. So the very basic idea of general relativity is not too complicated. First of all, you have to think of space and time as not two separate entities, but as one entity that acts as a four-dimensional object. We call it space-time because we're not very creative at naming things. Additionally, it turns out that space-time gets deformed by mass. So in this picture I have here, this grid is supposed to represent space-time, though again, remember space-time in reality is 4 dimensions, 3 space, 1 time. And you can see that it curves around planet Earth, and then the moon kind of is writing this curvature. So this curvature turns out to be what we perceive as gravity. So kind of a dirty secret of physics that we discovered in the 20th century is gravity isn't a force in the same way that the other forces are. Gravity is more a manifesting effect due to the geometry of the universe that we live in. So general relativity has done many things and has many great predictions that have been verified. One of them, the one that is of interest to us, is gravitational waves. So gravitational waves are extremely tiny ripples in the curvature of space-time. And I'll give you a better idea in a few minutes how tiny that is. They travel at the speed of light, and they stretch and compress space. So what does that mean? If you had a gravitational wave pass through this circle of dots that I have here, so this is just a circle of test particles, what would happen is this. And the interesting thing about this is that the dots themselves are not actually moving. This is the gravitational wave actually distorting the distance between the points. So all of these points here are completely stationary. These were predicted in 1915 by general relativity, Albert Einstein, but it took 100 years to detect them. Einstein himself, I believe, even thought, these effects are going to be so small that we're never going to be able to detect them. And they're generated by accelerating non-spherically symmetric masses. A really simple toy model that I like is you could think about a beach ball. And if you had a beach ball, a perfectly spherical beach ball resting in water, and let's just pretend that there's no friction because this is physics, so we ignore the real world and say there's no friction. If that beach ball were rotating, you wouldn't see any ripples in the water. But if you had something on there to break that spherical symmetry, so say that the little annoying thing that you use, you pull out to blow the ball up, deviates from a sphere, whenever that dips into the water, you're going to get ripples. You could think of gravitational waves as the same thing. When you get a mass that's not spherically symmetric and it accelerates, it creates ripples in an analogous way. I specifically look for gravitational waves from what are called compact binary mergers. So a compact binary is, it sounds more complicated than it really is. It's just a binary star system, so two objects that are orbiting, some common center of mass, and both objects are compact, which is just a measure, basically just a way of saying they're extremely tiny and very dense. So examples that you may have heard of are black holes. Black holes are compact objects, or neutron stars. Neutron stars are stars that weren't quite massive enough to become black holes at the end of their life. And a fun fact about those is a tablespoon of neutron star matter weighs as much as, I want to say, 9,000 pyramids of Giza. So it is extremely dense matter. So when you get two of these compact objects in a binary orbiting each other, the system of the binary is not spherically symmetric. And so they're going to lose energy to gravitational waves. They're going to emit gravitational waves. And it turns out that and they lose energy because gravitational waves contain energy. So, to emit them, that means the energy must come from the system. And it turns out that the rate at which they lose energy is proportional to the frequency of the binary. And so you get this runaway process where they lose some energy and the orbit shrinks, and then they lose more energy and the orbit shrinks more, and they lose more energy and the orbit shrinks more, and they speed up this entire time. So it becomes a runaway process where at the very end, you have very high frequency, very fast moving collision of a compact binary. So the very first one that we saw was the merger of two black holes. It was a binary black hole. Each black hole was roughly 30 times the mass of our sun. And by the time that they actually collided, in spiraling, they were traveling at about a third of the speed of light. So these are extremely energetic explosions in space, and these are the only systems that we have discovered gravitational waves from so far. And this is where I'll give you a sense of how tiny it is. The gravitational waves from the system I just described, the 30 solar mass black holes slamming into each other, moved particles in a circle like that picture I showed you, less than the radius of a proton. So it took this extremely energetic system to move our detector by less than the radius of a proton. So they're very tiny. This is why Einstein thought we might never detect them. So just quickly, I think I'm going too slow, so I won't spend too much time on this slide, but this is an example of what a typical gravitational wave waveform would look like, where you have two compact objects that are roughly the same mass, and you could see that the frequency increases as it gets closer to this maximum, and the amplitude increases as it gets closer to this maximum. So this is as the binary is speeding up, and then finally colliding and merging into something new. And the takeaway from this slide is that the binary itself has a very large impact on what these waves look like. So if instead both of these were larger, you could see that you don't get as high of a frequency as you do here. If one was smaller and one was larger, you could see that you get a very, very high frequency. So the point here is that just from observing these gravitational waves, we can extract a lot of information about the source that's emitting them. So how do we detect these? So we have these large-scale interferometers. If you don't remember interferometry from freshman physics, don't worry, I didn't either before I started working on this project, so I'll walk you through it. The idea is a laser is shot here into a beam splitter. It travels down these two perpendicular paths. These are mirrors, basically. It will go through, bounce off of this one up here, come back, same here, and then go down and recombine here at PD, a photodiode. If they travel exactly the same distance after they merge and then they rejoin, then they will completely cancel themselves out, because light is a wave, and this is just some weird wave effect that was discovered. If they, however, travel different distances, then they won't completely cancel out. And so you can see how we might use this. So as a gravitational wave were to pass through, it'll wiggle the arms like this, and then we can determine if something came through based on the photodiode output. So these things are extremely tiny, like I said, so we use very, very large detectors. We have 4 operating at the moment. There are 2 LIGO detectors, which LIGO is the collaboration that I'm a member of. One in Hanford, Washington, which is pictured here because I'm from Washington State, so I always have to show this off. And one from Livingston, Louisiana, and then a detector called Virgo in Italy, and a new detector called Kagra in Japan. And to give you a sense of scale for this picture, each of these arms, so this is the site right here. I think you can see my mouse. This is the site right here. And then these are the arms, like this is the main site. These are the arms that the laser gets shot down. And each of those arms is 4 kilometers or, roughly 2.5 miles long. So how do we actually analyze this data? It's a very basic idea. We take the data and basically just slide a waveform along it that we want to look for. And it turns out this is a convolution, a sliding dot product. It turns out that the output of this, if you transform the data correctly, which we won't go to, is proportional to the probability that there is a signal in the data. So in other words, when you see this big peak down here, this is the SNR, it's the output of just this sliding dot product. That means that it's pretty darn likely that there's a signal that matches that particular waveform at that spot in time. Now, the complication comes in that we don't know what waveforms we're going to find. We don't know what we are going to see in the data before we actually look at the data. So we have to do this roughly 1 million times. And so it becomes a very computationally costly endeavor. And then finally, just a real quick aside about the search I'm doing. With my collaborators, we're searching for a new type of source that I can answer questions on if people are curious, but the basic idea is that you can add a parameter to gravitational waves to account for some physical behavior that we don't expect to see from black holes or neutron stars, but some theoretical systems may have. And it makes the LIGO production searches completely insensitive to those signals, is what we found. So I think I'm short on time, so I'm not going to dive into what these plots are. I apologize. But that's the background and the physics of what I'm searching for. And again, I'm searching for a new type of compact binary merger, gravitational waveform, that the production LIGO searches, the collaboration big publication searches would be completely insensitive to. It's a very theoretical project, let's look and see if these are out here. Okay, now stuff that's actually relevant to the computing. So a high level view of this analysis workflow. So again, this is where I'll talk about this specific analysis that I ran using 6 months of data. So for inputs, I had LIGO Hanford detector data at 16 kilohertz and roughly 100 days of it. Same with data from the LIGO Livingston detector. And we only used these 2 detectors for this analysis. And we searched for about 500,000, about 500,000 different signals, sampled at 512 hertz that varied in length from 1 to 100 days. And the general workflow, we would divide up into 5-day chunks just because we've experimentally found that going much above that becomes untenable in terms of just because we have to do some data reduction in the middle. And if you analyze too much data at once, then you get too much data volume before the data reduction step can happen. So the workflow on each 5-day chunk is you first measure the frequency spectrum of the noise, where we decompose the waveform. So we search for 500,000 templates, but we use a singular value decomposition and some other neat tricks to actually filter the data against fewer waveforms. Sorry, I said templates. Template is our jargony word for waveform. Actually filter the data. So this is where we actually do a sliding dot product of these 500,000 different waveforms against 100 days of detector data from 2 different detectors. That is where the overwhelming majority of the computational cost comes from. And then the rest is aggregating statistics and assigning significance and performing data reduction. So because we definitely do not need all of the intermediate data products that we produce. The data products that we do keep are the decomposed waveforms. So this is our largest source of disk usage. We decompose the waveforms and again do a few tricks, like only sample the waveform as much as it needs to be sampled in order to resolve the frequency behavior and that sort of thing. But to do this, that means we have to actually store the numerical waveforms instead of generating them in memory. And each set of 5 days takes up about 50 gigabytes of space for this particular analysis. It should be noted that LIGO collaboration analyses are larger than this in multiple ways. One, there's more waveforms that are searched for, and two, it searches more detectors. So this is a large amount of disk space that gets used. And then the reduced filter output, and this is about 10 gigabytes per 5 days of data. And then the final results only take 100 megabytes, and that's an upper limit. So the final results are very tiny, and what we ended up doing when running on OSG is backing up decomposed waveforms elsewhere and just leaving the reduced filter output and final results on the login node. How am I doing for time? Do I need to wrap this up in 2 minutes?
You have, I'll give you another 2 minutes to wrap it up, and then we'll take it for questions.
Perfect. Okay. All right. So just a couple of comments about search computing in general, and then some stuff about actually using OSG. So as maybe you guessed, gravitational searches naturally fit high throughput computing workflows. We use internally the HT Condor scheduler. LIGO specific resources are available, but are limited. And one of our challenges moving forward is trying to be able to use more abundant resources, which we have noticed most resources are high performance computing clusters. OSG is perfect for this because you guys have already performed so much of the legwork to map these high throughput Condor workflows onto whatever is required for other clusters using different schedulers. It still took us roughly about 200 hours of development on our analysis itself to take advantage of this. So there's still a lot of development room for the LIGO people. It's possibly to not write resources for some other gravitational wave analyses, but it's perfect for searches. I analyzed the data using 2 workflows. I used the Open Science Pool to do, to be honest, the vast majority of it. And we used actually cluster-specific submissions using allocations, which Matt here was super helpful with. He was our point of contact. What I mean by that is we had an allocation through Stampede 2 at TAC in Texas. And Matt worked with us to set up functionality that I believe only one other person used before us, to be able to specify, I actually don't want to submit to the open pool. I want to submit to this specific cluster, and I want to use this specific allocation, which was very helpful. And we ran into some growing pains with that, but I think it came a long way and it was extremely helpful, and I hope to use that workflow again. Like I said, most of it, we actually ended up running on the Open Science Pool, which was fantastic. It took typically 3 days or less when nothing was going wrong to analyze each of these 5-day chunks. So my wish list, the things that, the number one thing that I needed that I had to go back and forth with OSG support on a lot was disk space. Even trying to write down in the beginning, oh, this is how much disk space I think I'll need long term, turned out to be untenable because sometimes things broke and before the data reduction step, and it took a while to fix it. And so there was some back and forth on that, and I ended up removing those waveforms that I talked about earlier and storing them on my own machine and Google Drive and stuff to back them up. That's the 50 gigabyte files that there's like 20 of. It would be great to come up with a system for that, to come up with come up with a more streamlined process of going about that. And then that would be the number one thing I'd say would be very useful for LIGO people. And the number two thing is less useful. I don't even really care, but I sort of care. It would be nice to have. The gravitational wave field is extremely competitive right now. And a lot of people are starting to work with small groups to search for new things, which is exciting, new physics, yay. But as a result, the fear of being scooped is very real. And it would be helpful if there were a way to make those public web pages not public. It's by no means a deal breaker if not. But here's my list of collaborators. Thank you for listening to my rambling. Sorry for being 2 minutes late and probably running late.
Okay, no worries, Cody. Thank you so much for your presentation. We have I'll give about a minute for any questions. If people want to ask something, they can raise their hand. But I can start by just commenting on your last point of disk and the web page, there are ways to address this as a OSG Connect user, and happy to have a conversation with you separately after this this conference. Just letting you know.
That'd be great. And let me say, first of all, real quick, just every interaction I had with the support was fantastic. This is, I hope this does not come across as a critique. Like everything worked out perfectly.
We understand completely.
Okay, good.
But thank you for raising those topics, because we heard this before from other people as well. In any case, are there any questions for Cody?